Alright, y'all, so today's going to be all about physics, specifically acceleration, velocity, and speed, but we're going to be looking at those things in the context of calculus. So, first thing, so let's start with an example here. Let's define right to be the positive direction. And in addition to that, let's say we have a moving object like Mr. Cookie over here, and say he is moving on to the right at a gradual pace. And he's really booking it. He's really booking it. Let's say, being the little speed demon he is, he managed to go from 0 meters to, let's say, 30 meters in 3 seconds. And he did that in a steady manner. So 0 to 30 in 3 seconds flat. Now, someone tell me, because he did that in a steady manner, how should I connect those dots?
Straight line.
Yes, exactly. A nice straight line. So good. Next question. How fast was he moving to the right? In other words, what was the rate of change of his position? The velocity.
0.
10 meters a second, right?
Yes. He went 30 in 3 seconds. 30 in 3 seconds. In 10 seconds in a steady rate. So positive 10 meters a second. Okay, that indicates he was always moving to the right. So, to follow up on that, what's the rate of change of his velocity? His acceleration? If he's always moving, or if he was always moving at 10 meters a second, then what was the rate of change of his velocity?
There would be no rate of change, right?
Yes, exactly. No rate of change whatsoever. So 0. So we had some rate of change for position, we had none for velocity, and these graphs kind of build off each other.
Okay.
Any questions so far? Okay. Now, importantly, and just to recap from what we've been doing so far, what is positive 10 visually in the context of this graph right here?
What is positive 10?
Yeah, what is positive 10 but in the context of this graph?
Would it be the slope of that graph?
Yes, it's the slope of this line segment, the steepness of this line segment. Everywhere. Same steepness because it's a straight line. Same steepness everywhere. Alright. Well, follow-up question. What is 0 in the context of the velocity graph?
0 would be the slope of the velocity graph.
Yes, the instantaneous steepness of this graph. And it turns out, because it's a nice flat line, it has 0 steepness everywhere. So, generalizing this gives us a nice definition for instantaneous velocity and instantaneous acceleration. Let's say I have not a nice position versus time graph. Let's say I got a very curvy one. Say like this. And let's say this is the point in time, let's call that timestamp A. The instantaneous velocity at timestamp A, as you've seen already, is just going to be what? The velocity of A, I can define that as?
The slope of the line tangent to that point, right?
Yes.
Okay.
And the definition of slope of tangency
is the derivative.
Yes. Instantaneous velocity is just defined to be the derivative at that point.
Okay.
Likewise, let's say I don't have a nice acceleration graph. Let's say it's curvy. Let's call that timestamp A. Let's say I want to find the instantaneous acceleration right there.
Wait, are we looking at the acceleration graph right now or the velocity graph?
Good catch. Yeah, this should be the velocity graph. Good.
Okay.
So we got a curvy velocity graph. What is going to be the acceleration at this point?
The derivative of the velocity graph.
Yes. So the acceleration at timestamp A is just defined to be the derivative of velocity evaluated at A. like so.
Yeah. Makes sense.
We good? Cool. Alright, and that's just at any point in particular. Now we can generalize this. We've got a nice definition of velocity and acceleration. So, velocity at any point in time is just defined to be the derivative of position at any point in time. And likewise, acceleration is divided by the slope of the velocity at any point in time. Yes? Well, this guy is the same thing, notationally. Is that right there? And now if I just do a little substitution thing, I can take this thing, S prime, stick in right there. So I get the derivative of position. And the way we abbreviate that is just S double prime of t. This is what's called the second derivative. You know, we've alluded to it in class already, but now we're going to make it explicit. Second derivatives, third derivatives, fourth derivative. These are what are called higher order derivatives. All right.
That's a quick question, though.
Yes.
I forgot what the 3 horizontal lines means instead of the 2 horizontal lines.
So when we're doing this just means we're giving a definition.
Okay.
We're not discovering or deriving something. It's just something we're making up. So we're defining instantaneous velocity to be the derivative of position. We're defining acceleration to be
Okay.
the derivative of the slope of velocity.
And the derivative of the slope of the velocity is equal to velocity. Okay, I see what you're doing now. I see.
All right. Before we move on, let's get clear on how to operate with higher order derivatives. So let's say we have this function. And now I can do this on the back of that sheet I gave you.
Okay.
Let's say this function, let's say f of x is equal to x cubed. How do I find f double prime of x and the third derivative of x? By the way, guys, when we go up beyond the second derivative, we don't want to keep writing apostrophes. So we just start denoting it with open parentheses, close parentheses, number, and that's how we go beyond the second derivative. All right, so take a minute to grapple with that. All right, we done? We done?
Yeah.
All right, so Mr. Jordan over there, tell me what you did for your first derivative.
So the first derivative, I just said I used the exponent 3 to move it down next to the x, so I said 3 times x, and then I subtracted 1 from the exponent to make it a 2, so
Yes.
it's 3x squared.
From there, what'd you do?
Onto the second derivative,
Yes.
I took the derivative again and multiplied the 3 by the 2 to make it 6, and then I subtracted the 2 exponent by 1 to just make it 6x.
Exactly, it's just another power rule application. So that is part of our answer.
Yes.
And then finally, Susan.
That's 6.
Yes. Third derivative
It's just 6.
is just 6. Very good. So, just keep in mind, when you go beyond the second derivative, notationally, we got to do it like this. Don't write 3 apostrophes, because that quickly becomes tedious. All right. So, moving back to some physics. I want you guys to take a minute or two to try this problem. So, get on the back.
Okay.
Let's say this is example number 1. Here's a car's position is given by the following equation. The position at any time is negative 8 times t squared, let's say plus 66t. So, 2 parts to this question. Find the velocity at the 30-second time step, and also find the acceleration at the 3-second time step.
The position is negative 8t squared plus 66t.
Yes, that's
Okay.
correct.
Okay.
Alright, so how do you all do with that?
So in order to do part A, you'd have to take the first derivative of the position, and that would give the velocity. The first derivative of s of t would be negative 16t plus 66.
Exactly. So that's your velocity at any point in time.
Mm-hmm.
So for this particular point in time, what do you do?
We have to solve for a v of 3, so we put 3 for a position of t, so that'd be negative 16 times 3
48.
plus 66, and that equals negative 48 plus 66, and I believe that's 18 meters
Yes.
a second. Or,
That's what I thought.
You concur in the corner?
Mhm.
Okay, cool. Positive 18 meters a second. Alright, and same deal for B. What do you guys get for your acceleration function?
so in order to do the acceleration, we would need to take the derivative of v of t, so that would be just negative 16.
Right. It's always negative 16.
Yes.
Now let's say this is in meters and we're measuring in seconds as well, so it's going to be negative 16 meters per second squared.
So I have a question.
Yes.
If acceleration is meters per second squared and velocity is meters per second,
Mhm.
how would we measure position?
In meters.
Just in meters?
Right, so remember how we measure position. We need two things. We need a reference point, and we need to define whether right or left, up or down, is positive or negative. So in all the problems we do so far, we're always choosing right to be the positive direction. So we choose our reference point, let's say at the origin or wherever, and if we define right to be positive, then if we go a certain number of meters to the right of that, it's positive, let's say 10, to the left would be negative.
Okay.
But yeah, position is just like velocity and acceleration. It's a vector quantity.
Okay.
It points from the reference point to whatever point you're going to. All right, what if I asked a follow-up question? And what does that negative sign mean?
It's decelerating.
So yeah, that's the physics explanation. It's always decelerating, but what does deceleration mean?
It's going into the opposite direction.
Coming to a stop.
It doesn't have to stop. It doesn't have to be going in the opposite direction. So let's look at the graph of velocity for this problem. What is this graph going to look like? Negative 16t plus 66.
Okay, so the y-intercept will be at 66,
Yes.
and then it will have a downward slope of 16.
Yeah, it's going to hit the t-axis at some point. 4-ish,
Yeah.
give or take. Let's keep going like that. So the velocity is always decreasing, right? Well, that doesn't mean it has to stop moving. In fact, it only stops moving at one point. That point right there. But when it's going from here to here, let's say it's still moving to the right. So it's going at positive 66, positive 50, positive 30, positive 10, 0, then it comes to a stop. Then what does it do from here to here?
It's going in the other direction.
Yeah, starts moving in the other direction, ramping up its speed in that direction.
Right.
So that's what's going on here. Velocity is always decreasing, but the speed, and we'll talk about speed more in a bit here, that's not always decreasing. The speed decreases from there to there, then comes to a stop, and then the speed increases from there to there.
Okay.
But it's moving it to the left, in the negative direction. But yeah, negative sign always means the velocity is decreasing. Alright, any questions about that? Alright, try another problem. Example 2. Say it goes something like this. Alright, so example 2, let's say a particle's position is given by this function here. want you to take a couple of minutes to go ahead and try to find the acceleration at the point in time when the velocity is 0. Alright, so have some fun with that for about a minute or two. Alright, do we settle on some answers?
Yes.
Alright, does someone want to come to the board and work this for me?
I'll try it out.
Alright, Mr. Sailor Moon.
Yes. Okay, so the first thing we're going to have to do, and I apologize if my handwriting is going to be pretty bad, I'll try to make it as neat as possible. I'll first take, first velocity is the first derivative of s of t, and that will be 3t squared minus 6t minus 9. And I'm going to also just take the derivative of this again to find the acceleration, because I'll need that for later. And a of t equals the derivative of this, which is 6t minus 6. So since the question is asking whether I should find the acceleration when the velocity is 0, we need to solve for this whole thing to be 0. So I noticed that these are factors of 3, so the first thing I'm going to do is take a 3 and factor it out of t squared minus 2t minus 3. And then I can use binomials to find out that that is 3 times t minus 3 times t plus 1. Now that gives us two possible answers of the t being either 3 or negative 1. Time can't be negative, so negative 1 can't be a possible option. So t must be equal to 3. And so I put 3 back into the acceleration over here, and a of 3 would be equal to 18 minus 6, which equals 12 meters a second squared. Did I do it right?
Yes, that's good. Great. One small thing though is just say this equals 0.
Oh yes, forgot to put that.
This thing equals 0 when t equals 3 and t equals negative 1, but like you said, we throw away the negative because we don't want negative time.
Okay.
That's not a thing. Cool. Alright, thank you, Jordan.
Yeah.
Alright, y'all, so let's talk more about the relationship between velocity and speed. Now, colloquially, we talk about these things as if they're the same, right? But in physics and calculus, in science, they're not quite the same thing. So velocity doesn't equal speed. The way we define velocity, the way we define speed, is the speed at any timestamp. Let's say the timestamp t equals a. That's just defined to be the velocity evaluated at a. Then you take the absolute value. If you're in one dimension. If you're in 2, you take the Pythagorean theorem. 3, Pythagorean theorem. But in one dimension, all you just do is take the absolute value. This is how we define speed. So, imagine this scenario here. We've already seen the shape of this graph in the previous example. But let's imagine now in a different scenario. Let's say, I have a marker. I throw it up in the air. I catch it right back at the same spot I released it from. And we'll say upwards are positive direction. That object, marker, at the greatest speed right when it left my hand, then it reached its maximum height, became 0.
And is this a velocity graph we're looking at, or a position graph?
This is a velocity graph.
Okay.
So velocity, time, maximum speed at the release point, and also maximum speed at the ending point. But why is velocity negative here? I defined up to be which
direction.
Which direction to define up to be? The positive direction?
Going up,
You said
negative
the
coming down.
x-axis was when it hit your hand, right?
Yeah, I mean, if this is my velocity graph, then it reached its maximum point.
That's there.
That's when its velocity is 0.
Oh, when it reaches its highest point and its velocity is 0?
Yes.
Oh,
Okay.
Velocity is 0 is always at max height.
right.
Okay.
Then it's coming down.
Yes.
So this makes sense because if it's still moving at max height, then by definition it's not max height.
Got it.
Right.
Right.
All right. So I defined up to be my positive direction. So that's why even though it's moving at the same speed at the catch point as it was when it was at the release point, it's not the same velocity. It's just the same magnitude but in the opposite direction. So I need that negative sign. So for that scenario, velocity is always decreasing. And let's just say, put some numbers here. Let's say that was the 3 second mark. Now someone help me out here. How would the graph speed look like? Given the graph of this velocity, and given our definition of speed.
Okay, wouldn't the speed look like that exact same thing, but instead of the values below the x-axis, it'd just be flipped above?
Exactly. What happens when you absolute value a negative number?
It becomes positive.
Yeah, so positives, here, stay where they are. Negatives get flipped, perfectly reflected over the t-axis. So we get this nice little V shape, like so. So speed is never negative. That's the takeaway from that. Okay. So just for your notes, note that velocity always decreased. For this picture. But here, not so. Speed is decreasing on what interval?
From 0 to 3?
Yeah, from the 0 second mark to the 3 second mark. It's increasing on what interval? How would I put that in interval notation?
3 to positive infinity?
Yes. 3 to positive, well, technically it's going to hit your hand, so there needs to be some timestamp.
Right.
So yeah, let's go ahead and call that. Well, what would be the timestamp? If it reaches max height at 3 seconds, if there's no air resistance, let's say, then when did it come back in your hand?
6 seconds.
Right, it's a perfectly symmetrical scenario.
Okay.
So 6 seconds there, 6 seconds here. So it's increasing on this interval, like so.
So technically this would be a definite line segment, right? It would have a start and a stop from 0 to 6?
Yes,
Okay.
for this scenario. But for other scenarios, it doesn't have to be the case.
Right.
For example, you could have an object, throw it up in the air, but then you pull your hand away. It's going to fall a further distance. Maybe it falls forever in some weird universe, but yeah, it doesn't have to be perfectly symmetric. Like that. All right. I want you all to work that first problem on that sheet I gave you. So this is going to be number 1. And it goes, let's see. You're going to have a nice equation. S of t is 2t cubed minus 15t squared plus 24t plus 1. Go ahead and start with part B and work through part E. Okay. We'll take like 5 minutes for that. All right, so picking back up with this problem. Someone tell me, what was this position function? It was a cubic.
Yes. S of t equals 2t cubed minus 15t squared plus 24t plus 1.
Like that?
Yes.
All right. So we're going to skip part A. We're going to look at part B. What's part B asking for?
It's asking when is the particle at rest?
All right. When something's at rest, what information do we automatically know right off the bat?
That the velocity is 0?
Yes. In math and physics, anytime to rest, that means at that instant velocity is 0. So that's for that one particular point in time. So what can I do to solve this problem? If I know the particular point time has to give you velocity is 0, I need to set what equal to 0?
The first derivative of the position.
Yes, velocity is the first derivative of this guy, which ends up being what?
6t squared
Minus 30.
minus 30t
Yeah, go ahead and read off.
plus 24.
So 6, negative 30, 24. And you have several ways of solving for t from here. You can do a quadratic, you can factor this guy. But what would be the easiest way to solve for t with this guy?
Let's first factor out the common denominator of 6 between each
Yeah, look, anytime you have numbers that have some factors in common, that should automatically be a trigger to pull out that common factor. So, t squared minus
5t plus 4.
plus 4, yes.
4.
That equals 0.
Okay.
So, hopefully this guy factors nicely. Does it?
Yes, it would be t minus 1 times t minus 4.
And that equals 0 by the zero factor property when what is true about t?
And t is 1 and t is 4.
Exactly. T is 1 and t is 4. So that solves this problem. But I want you guys to always get in the habit when you're doing computations to try to visualize it graphically as much as possible. What does the graph of v look like? If it's a polynomial with the highest degree of 2, that takes on what kind of shape?
Parabola.
Yes. It's always going to take on a parabola. So there's v, there's t. It has x-intercepts, or in this case t-intercepts at 1 and 4, yes? So 1 and 4, like that. Now, is this an upward-facing parabola or a downward-facing parabola?
It's
Positive t squared,
positive t squared.
negative 30, positive 24. What determines the direction of this?
Whether
parabola?
t squared is positive or negative.
Oh yeah, but whether the number in front of the t squared is
Positive or negative.
positive or negative. So positive 6 means this parabola
It's going upward.
is going up, which means it's going to cut through the t-axis at 1 and do a number like that, yes? Okay, good. What was part C asking for?
When is the particle moving to the right and to the left, and when does the particle change direction?
Okay, great. Now, guys, just remember, the thing that determines the direction something is moving in is always going to be your velocity function. If velocity is positive, that always means it's moving in the positive direction. And likewise, if it's negative, it's moving in the negative direction. So,
So positive means above the x-axis, negative means below the x-axis, right? Just to be sure.
yeah, our v values are being plotted on the vertical axis.
Okay.
So, vertical axis is always positive there. And it's always negative below the t-axis.
Okay.
So, now let's put that in interval notation then. So I believe right is our positive direction.
Oh no.
Oh no, good.
So this thing is, we already have the nice picture for us here. When is velocity positive? On what intervals?
On intervals 0 to 1, and I think 4 to positive infinity.
Yeah. So, close bracket, we're including 0. We're not including 1, so close parentheses. And we're going to union that with 4 to infinity. Like so. Our v value is positive here and here. So positive, positive. Alright. And now just likewise, when is it moving in the negative direction? To the left.
It would be parentheses 1 to 4 parentheses.
Yes. 1 to 4, non-inclusive. So, any questions about that?
So at points 1 and 4, the velocity would just be 0. So, like part B asks.
Yes, is at rest. So, it's not moving in just 2 instants in time, but at every other moment in time, it's either moving right or left.
Okay.
Cool.
And so it changes directions from right to left at 1, and then from left to right at 4.
Exactly. The moments where it's at rest is the moments where it transitions left to right or right to left. So, was that the next part of the question?
The last part was when does the particle change direction, and then part D is asking when is the particle's acceleration positive and negative and 0.
All right. So, the first thing you want to do is to get a nice function for acceleration. So, either in the corner. What is my acceleration function? And this is my velocity function.
Oh, but I can do that.
Are you sleeping off in
No,
class?
no. Okay, that's 12.
Yeah, I can't sleep off.
Okay, 12t minus 30.
Yes. I want to know when this is 0, yes?
It's positive, negative, and 0.
Okay, so let's start with 0. This thing equals 0 when what is true about t? Well, let's start off simple. It's 0 when 12t minus 30 is 0. So 12t equals 30. And so what's t as a nice decimal?
Can I answer? You still
2.5.
want my answer?
Yeah.
2.5.
Yeah,
Hey,
2.5.
you both can answer, yeah.
Okay.
3 over 12 and
That equals 5
Sorry,
over 2, which is 2.5.
yes.
Yeah.
2.5.
Okay.
So, if you want, we can get a nice graph for that. So there's my acceleration, vertical axis, t, horizontal axis. What does 12t minus 30 look like?
The y-intercept will start at negative 30.
Yeah, somewhere down here.
Yeah, and it will have a positive slope and hit the x-axis at 2.5.
Yeah. So it does some number like that, yes?
Yes.
So negative 30 right there, and 2.5.
And what's the slope?
Slope is positive 12. So, here is when it's at rest. Or when it's 0. Sorry, not rest. But this is when acceleration is 0. When is acceleration positive?
Any time after 2.5, right?
Yes.
When t is greater than 2.5.
Yeah. So we can say, open parentheses, 2.5 to infinity.
Okay.
And to finish it off, a is negative. Well, just the complement of that. So, start at 0, we include 0, and we go to 2.5.
So time, since you included 0, time at 0 is like a definite value?
Yeah, if I plug in 0 here,
Okay.
I get negative 30. So
Okay.
we do include 0.
Okay.
Okay, now I did part C and D and 3 parts so far. I've done with a graph. But also, you don't have to know the graph to do these problems. For example, if you just know the t-intercepts, you can do what's called interval testing to determine whether your graph's above or below the t-axis. So always keep that in mind. So the very last part of this question is dealing with speed. So to deal with speed, let's start with our velocity graph. It looked like so. T-intercepts at 1 and 4 respectively. If I want to go from here to a speed graph, someone tell me, what is this going to look like?
It looked like the same, but you'd have to take the absolute
Integral.
value of it.
It's the integral of.
It's the absolute value. The same from 0 to 1, but then 1 to 4 would be flipped over the x-axis.
When you absolute value negative values, they pop up and become positive. So this whole region here goes like this. We get 2 sharp points there and there.
Good.
And we got this kind of it's like a fish, right?
Yeah.
It's mouth open.
Nice.
But yeah. Alright, so when is this thing speeding up? Start with that part.
So speeding up would mean when it's x value
Is it speeding up from here to here?
that's
Yeah.
slowing down.
No.
Right?
Yeah, here to here is
Splitting up.
this is the graph of speed.
Okay.
So now we've got a nice definite graph of speed.
Okay.
The thing is going down, right?
Right. So
So-
it's decreasing.
So speed's decreasing from here to here.
So it's slowing down.
Yes.
Cool.
Slowing down from there to there. But it's speeding up from where to where?
I would say 1 to
So
basically the.
That was 1, that was 4.
the
What's this
halfway
middle point?
Would it be exactly 2.5? Oh yeah, when the acceleration is 0.
Right, we determined that acceleration was 0 at 2.5.
Okay.
And acceleration in the context of a velocity graph is just the what?
Is the integral of the acceleration or the
Well, geometrically, it's just a slope.
The slope.
And the slope right here at the top of this hill is clearly 0
Okay.
at 2.5. So, we got some speeding up going on from here to here. Where else do we got some speeding up?
4 to positive infinity.
Right. So, at these two regions, 2.5, or 1 to 2.5 and 4 to infinity, this thing is speeding up. And on the other hand, from 0 to 1 and 2.5 to 4, this thing is slowing down. So, let's always put this in interval notation like so. So let's say speeding up. So how do I write this in interval notation?
Speeding up 1 to 2.5. 1 parentheses 1 comma 2.5 parentheses union u 4 parentheses 4 comma positive infinity
Exactly.
parentheses.
Yeah, makes sense.
All right. What about slowing down?
Do you want me to say that?
Yeah, go for it, Mom.
Parenthesis, 1 to
Parentheses 1.
2.5 to 4
Start with the
and
first one.
0 to 1 union.
Okay.
0 to 1 and 2.5 to 4. That's all there is to it. Now again, I did all of these with a graph, but I tell you, you don't have to have a graph to be able to do all this. For example, note, if you want to do the speeding up problem without a graph, all you need to know, look at the pattern here. All the intervals for this one where we're speeding up, so let's say 1 to 2.5, do the little squigglies to indicate speeding up. And then from 4 to infinity, it was speeding up like that. In the first case, I went from a place where the velocity was 0 and then right here the acceleration was 0. And it was below the t-axis. Likewise here, this speeding up region, velocity was 0, but then it always increased above the t-axis. So these are always two giveaways for places where something's speeding up. If you just see this pattern numerically. And you can figure out a similar sort of pattern for slowing down. Alright, well that's just about it for velocity, acceleration, and speed. I'll give you guys some problems to do. They'll all be online. And we can talk about them next time.
So we're not going to do part A today?
No.
Okay. Sounds good.
Are we done?
Just a small bit. Just watch your paws. Chester, your horse.